Hi everyone, my name is Muhammad Nur Fahimi bin Jalaluddin, and today I will be presenting on developing an integrated smart agriculture system in Malaysia. Malaysia is a developing country with a tropical climate and a rich agriculture history, which is currently moving towards the fourth industrial revolution (IR4). The combination of AI and IoT technology in agriculture reflects a revolutionary change toward more intelligent and effective farming methods. The goals of this system is to improve crop yield, optimize water use, and energy efficiency for Malaysian farms. However, the implementation of this technology faces challenges related to environmental sustainability, cybersecurity risks, ethical risks over data collection, and societal acceptance of new technology. First of all, we will discuss the positive impact on society of the engineering activities in smart agriculture system. One of the most significant positive impact of smart agriculture is enhanced food security. The AI has improved the food security by weather prediction and pest prediction. This is crucial for production of export-oriented and staple crops such as paddy, palm oil, and tropical fruits. Among the examples that have been implemented is smart paddy farming in Kedah. The smart farming uses sensors that are placed in the field environment, water channels, and soil. The sensor collects data in real time on things like pH, nutrient levels, water temperature and humidity, and soil moisture and temperature. Besides that, smart agriculture also promotes skill development by encouraging the use of digital tools and platforms. Training programs that support adoption of these technologies contribute to broader digital literacy among farmers and agriculture workers. Next is improved farmer quality of life and efficiency. This is because the automation of labor-intensive tasks reduces the physical burden on farmers, allowing them to allocate more time toward family life, education, and community engagement. This shift can have a positive ripple effect on rural well-being and social cohesion. This is an example of function smart farming technique with use of AI and IoT. Next is positive impact on environmental. From an environmental standpoint, the positive impact we can achieve by using IoT soil sensor and AI irrigation to minimize water waste. This is because we can save the water waste by delivering water exactly where and when it's needed. Next is precision pesticide use reduces chemical runoff and protect biodiversity. For example, farmers can see early indicators of pest infestation, advanced detection, and use the pesticides more precisely and sparingly. Additionally, efficient machinery and logistics lower carbon emission. Among the examples of agriculture that produce lower carbon emission is Felda Smart Fertigation Project in Pahang, which is the smart fertigation system used automate irrigation and fertilization based on soil sensor. The sensor will monitor the condition of the soil and only apply nutrients when required. As a result of this, it will cut nutrient oxide emission by reducing excess fertilizer, uses solar power pump to reduce carbon dioxide, and this smart farm also convert organic waste to compost it rather than burn it to avoid open burning and methane emission. Here is some example of smart irrigation fertigation system. This system is one of the best way to irrigate and fertigate the plants at ground level where they require it the most. Next is the positive impact on economic. In terms of economic, positive impact we can achieve is improved revenue stability. One example of the smart agriculture is Madi Smart Greenhouse system in Cameron Highland. The smart greenhouse is focusing on high-value crops such as tomatoes, capsicum, strawberries, and others. The smart greenhouse integrates by using IoT-based climate monitoring, AI-powered crop management, and real-time mobile dashboard. Results from smart farming were better than those traditional ways. Usually, traditional farming generates estimate net profit 3,000 to 4,000 per cycle, where smart greenhouse generate 6,500 to 8,000 per cycle. Next impact is boost Malaysia agriculture export potential. This advancement boosts Malaysia's reputation in regional and international markets, strengthening the country's position in global food supply chain. Despite this benefit, several social risks emerge. First is inequality in technology, particularly for remote communities in East Malaysia, such as those in rural Sabah and Sarawak, with limited internet connectivity and poor infrastructure may prevent these farmers from accessing smart technology. Next is culture resistance. With the use of AI and IoT tools to replace generation-old farming methods may be met with resistance from traditional farming groups. Therefore, the pace of technology change must be balanced with cultural sensitivity and inclusive engagement. Next is negative impact on environmental. First is rise in e-waste. At the end of their life, sensor, gadget, and monitoring system can produce a lot of waste. Furthermore, energy consumption may rise due to the continuous operation of IoT devices and the energy demand of data centers. If this energy is sourced from non-renewable power, the environmental benefit in smart agriculture could be undermined by increased carbon emission. Next, furthermore, the negative impact on economy is high upfront costs, which include the purchase of IoT device, subscription to data, and maintenance can be expensive for farmers with limited capital, even with potential long-term benefit. In addition, the use of AI planning and decision-making introduce the risk of market volatility. If many farmers rely on similar predictive tools, they may all make the same decision regarding planting and harvesting schedule. This synchronization could lead to oversupply, causing price crashes and financial instability in the market. It also appears the risk in system failure and cyber attack, such as unauthorized access to farming system can lead to data breaches, manipulation of agriculture process, or even sabotage. This risk is not only threaten the financial of farm, but also compromise food safety and security. Next is the integration of sustainable design principle into smart agriculture system design. It is essential for Malaysia agriculture future. First thing first is carbon food reduction. Smart agriculture system can significantly lower their carbon footprint by adopting renewable energy sources, particularly solar power. This is especially in sun-rich states such as Perlis, Kedah, where solar panel can power IoT sensor and farm equipment effectively. Furthermore, through edge computing with local data processing, this is not only reduce energy consumption but also decrease system latency, enhancing operational efficiency. Additionally, AI-driven smart transportation tool can optimize delivery routes for agriculture input and produce, thereby cutting fuel usage and emission associated with logistics. Next is energy management for sustainable design principle. Usually, smart agriculture on various technologies such as sensor, drone, and cloud-based platform which consume energy. Thus, energy efficient design must be priority with the usage of low power IoT device, energy efficient data transmission, and the use of grid solar system. Furthermore, smart energy management system into farm operation dashboard allow farmers to monitor and optimize energy use in real time. For example, AI-based scheduling, irrigation, or greenhouse ventilation. Here we can see the type of sensor that be used in smart agriculture. Meanwhile, for water management, smart agriculture system must emphasize efficient water use. Among the example is automated drip irrigation system. This includes deploying automated drip irrigation system controlled by soil moisture sensor and weather forecast. This system can reduce waste up by to 50% compared to traditional irrigation flood. Next is wiring water harvesting system and closed-loop water recycling technologies. With use of AI, it can also support water usage forecasting, helping farmers plan their irrigation based on crop growth stage and predicted weather pattern. This is sample of schematic model for drip irrigation system. Smart agriculture system must also contribute to inclusive socio-economic growth, local capacity building, inclusive design, and community-owned networks. Next is ethical issue in smart agriculture. First is data privacy and ownership. Usually farmers with smallholder might not aware or have a legal protection for how third party gather, store, and use their farm data. Besides that is technological risk, cybersecurity, human error, and system failure will appear. For example, a malfunction in automated irrigation system or incorrect AI-generated recommendation could lead to crop loss and water waste. Additionally, poor cybersecurity measures could expose farm networks to hacking or data theft. Another major ethical issue is equitable access or digital divide between large agribusiness and smallholder rural farmers. Access to smart technology is often limited by cost, internet availability, and technical knowledge. This inequality risks widening socio-economic gaps and marginalizing vulnerability communities. Therefore, the resolution needed to overcome this ethical issue. For data privacy and ownership, robust data governance frameworks, farmers legally own and have full control access to their data. Additionally, before any data exchange or analysis is done, data anonymization and aggregation techniques should be used to protect individual identities. Next is technological risk. To mitigate such risks, smart agriculture system must be designed with fail-safe mechanism, manual override, and user-friendly interface to ensure farmer control. Furthermore, the government through bodies like MCMC and MADI should support the development of secure digital infrastructure which provide digital literacy training for farmers. This ensures that technical advancement does not outpace the user capacity to manage it safely. Next is ethical resolution for equitable access. The implementation of inclusive innovation policies. Inclusive innovation policies. Besides that, the Malaysian government should provide financial incentive, grants, and affordable access programs targeted at small-scale farmers. In parallel, private partnership can develop low-cost open-source smart farming tools and introduce a digital agri-module in vocational and tertiary agriculture education. So last but not least, the conclusion is AI and IoT is in agri can boost food security, economic resilience, and environmental sustainability. Yet, engineering activity must be carefully planned to avoid negative impact like digital inclusion, e-waste generation, or data misuse. By embedding sustainable development principles such as carbon footprint reduction, precision water and energy use, circular economy practice. By addressing ethical issues with strong governance and cybersecurity cybersecurity, inclusive culture, sensitive design that ensure the innovation enhance not disrupt society. Through thoughtful design and collaboration between engineers, policymakers, farmers, and community, Malaysia agriculture can enter a smart, fairer, and greener